This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 3 of From Pixels to Predictions. In today's episode titled Feature Detection Techniques, we're going to explore the fascinating world of identifying different types of features in images. So, whether you're a seasoned techie or just curious about how machines see the world, there's something here for you. Let's dive in. Your phone can recognize a landmark faster than you can say its name, yet it only sees flat pixels. In this episode, we drop straight into that split second when your camera locks onto a scene and quietly decides, these tiny spots, they're the ones that matter. Before your camera can recognize anything, it has to decide where to look. Not every pixel gets a vote. Some spots in the image are far more informative than others, and feature detection is the quiet referee that promotes those few from background noise to critical evidence. In practice, this means the system hunts for patterns that tend to survive change, a sharp corner on a street sign that's still visible at night, a textured logo that's recognizable from far away, or the circular outline of a traffic light seen from an angle. These become anchors that later algorithms can track, match, and describe. Different techniques specialize in different trade-offs. Some favor precision but are slower, others are lightweight enough to run on a cheap drone camera. In the rest of this episode, we'll unpack how those trade-offs are engineered. Some of the most widely used detectors didn't come from flashy deep networks, but from surprisingly simple rules engineers tuned over years of trial and error. Harris looks for strong intensity changes in two directions, great for crisp corners on signs and buildings. SIFT adds scale awareness, so a small logo and a billboard-sized version still map to comparable points. Orb trades some precision for speed and compact binary descriptors, which is why it shows up in mobile AR and low-power drones that can't afford heavyweight computation. Today's learned methods start here, then push further. When engineers talk about good features, they're not talking about beauty, they're talking about survival skills. A key point is valuable only if it can be reliably found again after the world has messed with the image, zoomed in, rotated, dimmed the lights, or shifted the viewpoint. That's why one of the first questions in feature design is, what kinds of abuse should our points withstand? Scale, rotation, and illumination changes are the usual suspects, but in real deployments, you also face blur from motion, lens distortion, and partial occlusions from passing objects. Classic handcrafted methods approach this by baking invariance into the math. They deliberately ignore fragile cues like exact brightness and instead encode more stable patterns, relative intensity changes, local gradients, or region statistics. That's how descriptors like SIFT tolerate a 3-time scale jump or a 60-degree viewpoint change while still matching reliably. But this robustness has a price: higher dimensional descriptors and more computation per feature, which limits how many points you can afford to process in real time. Modern learning-based approaches flip the workflow. Instead of specifying what should be invariant, researchers specify the task. For example, find points that match well across many views in this dataset, and let a neural network discover which image structures work best. Superpoint does this by jointly learning where to place key points and how to describe them, so the detector and descriptor are tuned to each other rather than designed in isolation. Systems like Lofter go even further, skipping discrete key points altogether and directly predicting dense correspondences between images, which is especially useful when texture is weak or repetitive. These capabilities aren't just academic. Google's visual positioning service fuses billions of such features into a global memory of the world, so a single phone snapshot can be localized within centimeters in mapped areas. Autonomous vehicles knit together overlapping features from successive frames to estimate motion and reconstruct 3D structure. AR frameworks balance heavy, accurate detectors for initial mapping with lighter, orb-style ones for fast tracking on mobile hardware. Your challenge this week: pick a real-world app you use, AR navigation, visual search, or a camera-based measuring tool, and notice when it fails to lock on. Tilt the phone, change the lighting, move closer or farther. Treat it like a stress test. Which conditions break its feature detection? The patterns you find will reveal which invariances its designers prioritized and which ones they traded away. Think of feature detectors as different kinds of chefs deciding which ingredients in a scene are worth keeping. In product search, Amazon's camera feature leans on logo corners, label typography, and distinctive shapes, so a crumpled cereal box still matches the pristine catalog photo. In sports analytics, systems latch on to jersey numbers and field markings to track players through fast motion and partial occlusion. Robot vacuum mappers don't care about your decor style. They favor edges of walls, door frames, and furniture bases that stay put across days. On factory lines, inspection cameras highlight solder joints, screw heads, and connector outlines, tiny, repeatable structures that flag defects when they deviate. In cultural heritage digitization, pipelines preserve carvings, cracks, and chipped edges on statues so 3D models can be aligned over years as damage progresses. Even simple panorama apps selectively stitch frames by trusting only those repeatable micropatterns, brick textures, window grids, tree branches that overlap cleanly while discarding bland sky that offers nothing stable to hold on to. As detectors evolve, they'll quietly reshape how devices notice the world. Learned features tuned to your home, office, or factory could act like personalized spam filters for reality, highlighting only what matters and ignoring the rest. In finance, phones might recognize receipts and contracts as fluidly as faces. In medicine, microscopes could flag rare cell patterns that humans overlook. The frontier isn't just more accurate matching, it's deciding which visual events deserve attention in the first place. As detectors grow more adaptive, they may start tuning themselves on the fly, reshaping what your devices consider noteworthy in each environment. One day, your phone could quietly learn that grocery shelves, receipts, and meds deserve extra attention, while background clutter fades, like a playlist that keeps refining itself around what you actually stop and listen to. Here's your challenge this week. Pick one real image from your life, for example, your desk, your street, or your kitchen, and implement 3 different feature detection methods on it: Harris Corner Detector, SIFT, or ORB if SIFT isn't available, and Canny Edge Detection. Run all 3, then screenshot and compare the outputs side by side, counting how many key points each method finds and noting where they cluster: corners, blobs, edges. Finally, tweak at least one parameter for each method, like the Harris threshold, number of orb features, or Canny thresholds, and observe exactly how the visible features and counts change, summarizing your observations in 3 bullet points. This was OwlUp, your daily step forward. To keep learning with structured courses and more insights, go to owlup.co. Until tomorrow!